You have looked at the night sky and wondered what lies beyond. Perhaps you stared at one particular point in space, somewhere in the constellation Sagittarius, never knowing that you were gazing toward the most violent object in our cosmic neighborhood. Something is there, something vast and hungry and impossible, something we finally managed to see. Astronomers unveiled the first image of the supermassive black hole at the center of our own Milky Way galaxy in 2022. This black hole is 4 million times more massive than our Sun, sitting 27,000 light-years away from Earth. The image revealed what scientists had theorized but never witnessed: a glowing ring of superheated gas surrounding absolute darkness. This is not just another astronomical photograph. This is evidence of something that should not exist according to our everyday understanding of reality. Here is where things become strange. When the Event Horizon Telescope collaboration compared this image to their earlier capture of the black hole in the Messier 87 galaxy, they discovered something profoundly unsettling. The two black holes look remarkably similar, even though our galaxy's black hole is more than 1,000 times smaller and less massive than M87, with observers noting that close to the edge of these black holes, they look amazingly similar. Why would objects separated by 55 million light-years, vastly different in size and mass, appear almost identical? The answer lies not in the black holes themselves, but in what happens to space-time around them. Think about a moment when you encountered something you could not explain. The feeling of certainty crumbling. That disorientation when the rules you understood suddenly change. This is what physicists experienced when they realized what these images truly mean. The similarity between black holes of different sizes suggests that general relativity governs these objects up close, and any differences we see further away must be due to differences in the material that surrounds the black holes. Einstein was right about gravity warping space-time, but he never imagined we would actually see it happen at this scale. Let me take you to the moment scientists first glimpsed inside a black hole. Not literally inside, because nothing escapes a black hole once it crosses the event horizon. But they saw something equally remarkable. They saw the structure that forms at the very edge of existence. In April 2017, 8 radio observatories positioned across 6 continents synchronized their observations. The Event Horizon Telescope is an array that links together 8 existing radio observatories across the planet to form a single Earth-sized virtual telescope. For 10 days, these telescopes stared at 2 targets. One was M87, a supermassive black hole in a distant galaxy. The image shows a bright ring formed as light bends in the intense gravity around a black hole that is 6.5 billion times more massive than the Sun. The other target was closer, much closer. Sagittarius A star, the monster at the center of our own Milky Way. The data they collected filled petabytes of hard drives. 5 petabytes. That is 5 million gigabytes of information. So much data that they could not transmit it over the internet. They had to physically ship hard drives by airplane from each observatory to processing centers at MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy in Germany. After collecting a total of 5 petabytes of data encompassing observations of both SGR A star and M87 star, hard drives full of recorded data were shipped across continents. One hard drive from the South Pole telescope could not be retrieved until December 2017 because there are no flights in or out during austral winter. What happened next took years. The data had to be correlated, synchronized, calibrated. Massive supercomputers worked to correlate the data, comparing the data streams between different observatories and converting that data into signals that a planet-sized telescope would see. Then, calibrating the data in a meticulous process of weeding out noise from sources such as instrumentation effects and the Earth's own atmosphere. Think about that process. These scientists spent years removing every possible source of error, every artifact, every distortion, to reveal what actually exists 27,000 light-years away. The first image of M87 star stunned the world in April 2019. The first image of a black hole at the center of galaxy Messier 87 was published by the EHT collaboration on April 10, 2019. But imaging Sagittarius A star proved far more challenging. The problem was motion. Imagine photographing a toddler running in circles versus an adult sitting still. Both images require the same exposure time, but one subject will be a blur. Superheated gas travels at near light speed and takes days to orbit M87 star, but only takes minutes to orbit SGR A star, creating motion blur, with the analogy being that if you have an adult getting their portrait taken with a long exposure, they're just sitting still. While for SGR A star you have a toddler running around, and you're trying to get their portrait with the long exposure camera, resulting in blur everywhere. The gas surrounding Sagittarius A star completes an orbit in mere minutes. During the time it takes to capture the image, the entire structure changes. The gas moves, brightens, dims, shifts position. Akiyama, who led the EHT's imaging team, developed a new algorithm to pair with those used to image M87 star, and researchers fed data into each algorithm to generate thousands of images of the black hole. Then averaged these images to generate one main image which revealed SGR A star as a glowing ring-like structure. They generated thousands of possible images from the data, testing different algorithms, different assumptions, different ways of interpreting what the radio waves were telling them. What emerged was consistent, a bright ring, a dark center, and something scientists did not expect. The ring is not uniform. One side glows brighter than the other. This asymmetry tells us something crucial about the black hole. It is spinning. From the enhanced brightness of the southern part of the ring, due to relativistic beaming of approaching funnel wall jet emission, EHT concluded the black hole spins clockwise as seen from Earth. Material on the approaching side of the black hole appears brighter because it is moving toward us at a significant fraction of light speed. This effect, called relativistic beaming, causes light to pile up in the direction of motion, making that side of the ring appear more luminous. But here is what makes scientists uncomfortable. Glowing gas orbiting around the black hole reveals a telltale signature, a dark central region called a shadow surrounded by a bright, ring-like structure, with a new view capturing light, bent by the powerful gravity of the black hole, which is 4 million times more massive than our Sun. That central darkness is not the black hole itself. We cannot see the black hole. Light cannot escape from within the event horizon, so the black hole remains invisible by definition. What we see is its shadow cast against the glowing gas behind it. This shadow has a specific size. EHT measured the black hole's mass to be 6.5 plus or minus 0.7 billion solar masses, and measured the diameter of its event horizon to be approximately 40 billion kilometers for M87 star. The shadow itself appears roughly 2.5 times larger than the event horizon. Why? Because light passing near the black hole gets bent by gravity, creating a region around the black hole where photons orbit before either falling in or escaping. This region is called the photon sphere. Now pay attention to what this means. General relativity predicts that embedded within this image lies a thin photon ring, which is composed of an infinite sequence of self-similar subrings that are indexed by the number of photon orbits around the black hole, with the subrings approaching the edge of the black hole shadow and becoming exponentially narrower but weaker with increasing orbit number. Light can orbit a black hole. Not permanently, because these orbits are unstable, but temporarily. A photon approaches the black hole at just the right angle and distance, and instead of falling straight in, it curves around the black hole. Some photons complete half an orbit before escaping. Others complete one full orbit. Some complete multiple orbits, each time passing through the hot gas surrounding the black hole, collecting more photons along the way. This creates something extraordinary. These subrings produce strong and universal signatures on long interferometric baselines, and these signatures offer the possibility of precise measurements of black hole mass and spin, as well as tests of general relativity using only a sparse interferometric array. Each successive orbit creates a narrower, fainter ring nested within the previous one. An infinite sequence of rings, stacked concentrically, each one a ghostly echo of the one before it. The photon ring is not one ring, but an infinite series of rings, each corresponding to photons that orbited the black hole a different number of times before reaching our telescopes. Scientists have not yet resolved these individual subrings. The current images show a blended brightness from multiple orbits. But they know the subrings are there, predicted by mathematics, confirmed by simulations, waiting to be detected with higher resolution observations. The breakthrough will result in a remarkable 50% increase in detail, sharpening images and observations of black holes and their surrounding regions. And when combined with existing images of supermassive black holes at 230 GHz, these new results will not only make black hole photographs 50% crisper, but also produce multicolor views of the region immediately outside the boundary. Have you ever stood at the edge of something vast and felt your sense of scale collapse? Perhaps at the rim of a canyon, or looking up at mountains, or out across an ocean. That moment when you realize how small you are, multiply that feeling by incomprehensible factors. The black hole at our galaxy's center could swallow our entire solar system and barely notice. Yet we see it. We have photographed it. We have measured how its gravity bends light from behind it into our telescopes. But imaging black holes revealed more than their shadows and photon rings. Scientists discovered that black holes have magnetic fields, strong ones, organized ones, fields that spiral and twist around the event horizon in structures we are only beginning to understand. In March 2021, the EHT collaboration produced the first polarized image around the black hole of M87, with an azimuthal electric vector polarization pattern found around the ring, consistent with dynamically strong magnetic fields in the accretion flow. Polarized light reveals magnetic field structure. When light passes through a magnetic field, it becomes polarized, meaning the electric field oscillates in a preferred direction rather than randomly. By measuring this polarization in the light coming from around black holes, scientists can map the magnetic fields. What they found surprised them. A new image from the Event Horizon Telescope collaboration has uncovered strong and organized magnetic fields spiraling from the edge of the supermassive black hole, Sagittarius A star. And seen in polarized light for the first time, this new view revealed a magnetic field structure strikingly similar to that of the black hole at the center of the M87 galaxy. Both black holes, despite their vastly different sizes and locations, show similar magnetic field patterns. These fields are not weak or random. There are strong, twisted, and organized magnetic fields near the black hole at the center of the Milky Way galaxy, and along with SGR A star having a strikingly similar polarization structure to M87 star. This shows that strong and ordered magnetic fields are critical to how black holes interact with gas and matter around them. This discovery points towards something profound. If black holes separated by cosmic distances show similar magnetic structures, then perhaps these structures are universal features. Perhaps all supermassive black holes organize magnetic fields in similar ways. These fields likely play a crucial role in launching jets, those enormous beams of particles and radiation that some black holes shoot across intergalactic distances. Then came something even stranger. While M87 stars' magnetic fields appeared to spiral in one direction in 2017, they settled in 2018 and reversed direction in 2021. The magnetic fields around M87 star flipped. The fact that the polarization pattern flipped direction from 2017 to 2021 was totally unexpected. Scientists watching the black hole over multiple years observed the magnetic field structure reverse its spiral direction. This should not happen if black holes are static, unchanging objects. But they are not static. The material around them churns and boils and streams inward at relativistic speeds. The cumulative effects of how this polarization changes over time suggests an evolving turbulent environment where magnetic fields play a vital role in governing how matter falls into the black hole and how energy is launched outward. The environment near a black hole event horizon is violent beyond imagination. Gas heated to billions of degrees, particles accelerated to near light speed, magnetic fields twisted by the rotating space-time itself. Something else happens in these observations. For the first time in EHT data, scientists have also detected signatures of jet emission near the base of the jet that emerges from the close environment of the black hole. M87 star launches a jet, a narrow beam of matter and energy that extends thousands of light years from the black hole. This jet is visible in many wavelengths, from radio waves to X-rays. But until recently, scientists could not observe the base of the jet, the region where it forms right at the edge of the black hole. The new observations detected faint emission from this region, providing the first direct look at where jets originate. Jets remain one of the great mysteries. How does matter swirling into a black hole suddenly reverse direction and shoot outward at nearly light speed? The magnetic fields appear to be key. This is significant because it suggests that the physical processes that govern how a black hole feeds and launches a jet may be universal features amongst supermassive black holes. Somehow, the twisted magnetic fields threading through the accretion disk channel energy away from the black hole, accelerating particles outward along the rotation axis. Consider what this means. Matter falling toward a black hole carries angular momentum. It cannot fall straight in. Instead, it forms a disk, an accretion disk, spiraling inward like water circling a drain. As the disk material moves closer to the event horizon, it moves faster. Friction between different parts of the disk heats the material to extraordinary temperatures. Near the black hole, the disk glows with X-rays and gamma rays. Further out, it emits visible light, infrared and radio waves. But here is the problem. For matter to actually fall into the black hole, it must lose angular momentum. Something must slow down the inward spiral, allowing material to cross those final kilometers and disappear beyond the event horizon. Magnetic fields provide the mechanism. They extract angular momentum from the disk and transfer it outward. They also tap into the rotational energy of the black hole itself through a process called the Blandford-Znajek mechanism, converting the black hole's spin into enormous jets of particles. This process is not gentle. The brightness peak of the ring has shifted by about 30 degrees compared to the images from 2017, which is consistent with our theoretical understanding of variability from turbulent material around black holes. The accretion flow is turbulent, chaotic, constantly changing. Clumps of hot gas orbit the black hole, creating bright spots that move around the ring over hours or days. These bright spots appear in different locations in images taken at different times. Now comes a question that troubles physicists. What happens to information that falls into a black hole? You might wonder why this matters. Information seems abstract, disconnected from physical reality. But in physics, information is fundamental. It is the pattern of matter and energy, the specific arrangement of particles that makes you different from someone else, the precise state of every particle, every wave, every field in the universe. According to quantum mechanics, information cannot be destroyed. This principle, called unitarity, is central to how quantum theory works. Black holes seem to violate this principle. The particles shed by black holes appear to carry no information about the interior contents, so if a 100-kilogram astronaut falls in, the hole grows in mass by 100 kilograms. Anything that crosses the event horizon falls toward the singularity at the black hole's center, where it is crushed to infinite density, obliterated beyond recognition. Its information should be preserved somewhere, but where? Stephen Hawking showed in the 1970s that black holes emit radiation. Due to quantum mechanical fluctuations near the horizon, black holes should emit radiation called Hawking radiation, a famous theoretical prediction that Stephen Hawking made in the 70s. Quantum effects near the event horizon create particle-antiparticle pairs. Usually these pairs annihilate immediately. But near the horizon, one particle can fall into the black hole while the other escapes. To an outside observer, the black hole appears to emit thermal radiation. Over immense timescales, this radiation causes the black hole to evaporate. Here is the paradox. Classically, all the information making the black hole has fallen inside, but Hawking radiation implies that the black hole emits thermal radiation, and this thermal radiation apparently carries no information about the things that fell in, since this radiation is generated in the vicinity of the horizon. Thermal radiation is random. It carries no information about what created it. If you burn a book, the smoke and heat carry information about the paper and ink at a microscopic level, encoded in subtle correlations. But Hawking's calculations suggested black hole radiation is perfectly thermal, completely uncorrelated with anything that fell in. This creates a catastrophic problem for physics. If information is destroyed in black holes, then quantum mechanics is wrong. If quantum mechanics is right, then something is wrong with our understanding of how gravity and quantum theory interact. For decades, physicists argued about which principle to sacrifice. In a landmark series of calculations, physicists have proved that black holes can shed information, which seems impossible by definition, and the work appears to resolve a paradox that Stephen Hawking first described 5 decades ago, with information now confirmed to escape a black hole. Recent theoretical work suggests that Hawking radiation is not perfectly thermal after all. Subtle quantum correlations exist in the radiation, correlations that encode information about what fell into the black hole. Within the string theory community, the dominant idea is that Hawking radiation is not precisely thermal, but receives quantum correlations that encode information about the black hole's interior. And this viewpoint received further support in 2019 when researchers amended the computation of the entropy of the Hawking radiation and showed that the radiation is in fact dual to the black hole interior at late times. The resolution involves something called holography, not the kind that creates 3-dimensional images, but a deeper principle about how information is stored in space-time. Among the strange things required is something called holography, an idea developed by 't Hooft and further by Susskind, with the idea being that the physics of the 3-dimensional interior of the black hole, where gravity plays a role, can instead be viewed via a mysterious transformation as physics just above the 2-dimensional horizon, described by two-dimensional equations that do not include gravity at all. This sounds absurd. How can three-dimensional physics be equivalent to two-dimensional physics? Yet mathematical evidence strongly supports this idea. The information content of a region of space is proportional not to its volume, but to its surface area. For a black hole, Jacob Bekenstein discovered that the black hole entropy is precisely 1/4 of the information capacity of a black hole. Entropy here measures information, specifically the information required to specify the exact state of the black hole. This entropy is proportional to the area of the event horizon, not the volume inside it. Think about this carefully. If you and I both fall into a black hole, the information about both of us, everything that makes us unique, gets encoded on the surface of the event horizon. The interior volume seems irrelevant for information storage. This implies something radical about the nature of space-time itself. Perhaps the interior of the black hole is not fundamental. Perhaps it is an emergent description, a way of interpreting information encoded on the horizon. This leads to black hole complementarity, a proposal that sounds like science fiction. Observers who fall into the black hole see the information located inside, while observers outside see the information being stored just outside, where it can later be transferred to Hawking radiation. And since the two classes of observers cannot communicate, there is no paradox. According to complementarity, what happens depends on your perspective. An observer falling into the black hole experiences a smooth passage through the horizon, seeing information fall toward the singularity. An observer remaining outside sees information smeared on the horizon, never quite crossing it, eventually re-emitted in Hawking radiation. Both descriptions cannot be simultaneously true in ordinary physics. But near black holes, where extreme gravity meets quantum mechanics, perhaps both are true in some sense. The falling observer and the outside observer literally inhabit different descriptions of reality, descriptions that never contradict, because the two observers cannot compare notes. Once you cross the horizon, you cannot send signals back out. But complications arose. In 2012, physicists proposed the firewall paradox. In 2012, the firewall paradox was introduced with the goal of demonstrating that black hole complementarity fails to solve the information paradox. The argument goes like this. If information escapes in Hawking radiation, then late-time radiation must be highly entangled with early radiation. But quantum mechanics forbids a particle from being maximally entangled with two different systems simultaneously. The particles crossing the horizon are also entangled with their partners in the Hawking radiation. This creates a problem. To preserve both quantum mechanics and information conservation, there must be a wall of high-energy radiation at the horizon, a firewall that incinerates anything trying to cross. This violates the equivalence principle, Einstein's insight that freely falling observers experience no gravity. An observer falling toward a black hole should not experience anything special at the horizon, at least not for very large black holes where tidal forces remain weak. But if a firewall exists, crossing the horizon means instant obliteration. No smooth passage, no interior to explore, just destruction. Physicists remain divided on this paradox. Some argue that firewalls must exist to preserve quantum mechanics. Others search for ways to maintain both information conservation and smooth horizons. The black hole interior from non-isometric codes and complexity has been formulated in recent work exploring how interior degrees of freedom are encoded in the quantum states on the boundary. Recent work explores quantum error correction, the same mathematics used to protect quantum computers from noise, as a way to understand how information inside the black hole relates to information outside. The key insight is complexity. Not just information content, but the computational complexity of transforming one state into another. Page curve calculations can be attributed exactly to complexity in toy models of black holes, and we will likely be exploring the consequences of these developments on quantum gravity for years to come. Decoding the information from Hawking radiation requires a computation so complex, so time-consuming, that it effectively cannot be done in practice, even though it is possible in principle. The information is there, encrypted in the radiation, but unscrambling it would take longer than the age of the universe. This might resolve the firewall paradox. The information is both inside and outside the black hole, but in different forms. Inside, it is localized and accessible. Outside, it is scrambled across the horizon and Hawking radiation in a pattern so complex that no observer could reconstruct it without performing an impossibly difficult computation. From the outside, the black hole appears to have an interior, because that description is simple. Describing everything in terms of scrambled quantum information on the horizon would be technically correct, but computationally intractable. Let me return to what we actually observe. The images of black holes show structures shaped by physics we are still struggling to understand. Black hole images display distinctive features, including a narrow photon ring composed of a stack of increasingly sharp subrings. And these subrings provide precise insights about the underlying space-time via their size shape and self-similar structure, while other prominent features include the shadow and inner shadow. But these also depend on details of the underlying emission. The photon ring encodes geometry. The shadow encodes the horizon. The inner shadow, a brightness deficit at the center of the direct image, encodes where the equatorial event horizon appears against the surrounding glow. New observations from the Webb telescope, captured in July 2024 and March 2025, including the telescope's sharpest image, yet of a black hole's surroundings countermanded previous theories, with nearly all of the infrared emissions, 87%, of hot dust in the Circinus black hole coming from the areas closest to the black hole, while less than 1% of emissions come from hot, dusty outflows. The James Webb Space Telescope, observing in infrared wavelengths, sees different structures than radio observations. Webb sees the hot dust, the donut-shaped torus of material surrounding the accretion disk. Observations and models suggest that the preferred component of infrared light is the heated dust in the funnel, making up the inner surface of the donut-shaped ring around the black hole. Most infrared emission comes from very close to the black hole, from the inner rim of the dust torus where temperatures reach thousands of degrees. What else lurks near black holes? Scientists believe the most likely explanation for periodic outbursts stems from a second, smaller black hole that is zinging around the central supermassive black hole and slinging material out from the larger black hole's disk of gas every 8.5 days. In 2024, astronomers observed a galaxy showing periodic fluctuations in X-ray emission, repeating every 8.5 days like clockwork. The pattern suggests a smaller black hole, perhaps 100 to 10,000 times the mass of the Sun, orbiting through the accretion disk of a much larger black hole. Each time the smaller black hole punches through the disk, it would eject another plume in a regular periodic pattern, and the observed outburst was likely a signal of a second, smaller black hole, orbiting a central supermassive black hole and periodically puncturing its disk. This discovery hints that accretion disks are not smooth and uniform, but can contain other massive objects. The findings challenge the conventional picture of black hole accretion disks, which scientists had assumed are relatively uniform disks of gas that rotate around a central black hole, suggesting that accretion disks may be more varied in their contents, possibly containing other black holes and even entire stars. Stars may orbit within the disk. Smaller black holes may spiral inward, eventually merging with the central beast. The environment near a supermassive black hole is more chaotic, more dynamic, more violent than simple models suggest. Intermediate mass black holes remain mysterious. Stellar remnants are often black holes with a size between 5 and 100 solar masses, while the centers of massive galaxies harbor supermassive black holes weighing more than 100,000 solar masses, with our Milky Way having a black hole with about 4 million solar masses, while giant elliptical galaxy M87 has one with several billion solar masses. Between stellar mass black holes and supermassive ones lies a gap. Intermediate mass black holes would weigh about 1,000 to 100,000 solar masses. Do such black holes exist? There are no observations that clearly confirm their existence, and the calculations are very inaccurate. Recent theoretical work suggests these intermediate mass black holes might form quickly near galactic centers. Medium mass black holes are likely to form quickly and frequently in the innermost regions of galaxies such as our Milky Way, with stars constantly forming in dense massive star clusters. And when these massive stars die, they leave behind stellar black holes which accumulate near central regions of clusters and orbit around the center of the Milky Way. So if this theory is correct, then the Milky Way would currently harbor dozens of intermediate mass black holes within a radius of about 600 light-years around its central supermassive black hole. Observations of movements of stars and gas around them have reported about 5 candidates. In May 2025, astronomers used NASA's Hubble Space Telescope with supporting observations from NASA's Chandra X-ray Observatory and the NRAO Very Large Array Telescope to pinpoint a wandering supermassive black hole using a tidal disruption event called a 2024 TVD. This 1 million solar mass black hole doesn't reside exactly in the center of the host galaxy, where supermassive black holes are typically found. And out of approximately 100 TDE events recorded by optical sky surveys so far, this is the first time an offset TDE has been identified. This black hole is prowling through the galaxy far from the center, revealing itself only when it devours a passing star. These wandering black holes likely result from galaxy mergers. When two galaxies collide, their central black holes sink toward the center of the merged system. But sometimes gravitational interactions eject one black hole, sending it wandering through the galaxy. Tidal disruption events hold great promise for illuminating the presence of massive black holes that we would otherwise not be able to detect, with theorists having predicted that a population of massive black holes located away from the centers of galaxies must exist, but now we can use TDEs to find them. You might be asking how we know black holes exist at all. We cannot see them directly. They emit no light. Yet the evidence has become overwhelming. The observation of several stars orbiting Sagittarius A star, particularly star S2, have been used to determine the mass and upper limits on the radius of the object. And based on the mass and precise radius limits obtained, astronomers concluded that Sagittarius A star was the central supermassive black hole of the Milky Way galaxy. Stars orbit something at the galactic center. Their orbits follow precise Keplerian paths, shaped by a point mass of 4 million suns. But that point mass is invisible and extraordinarily compact, packed into a region smaller than the orbit of Mercury. Reinhard Genzel and Andrea Ghez were awarded a half share in the 2020 Nobel Prize in Physics for their discovery that Sagittarius A star is a supermassive compact object for which a black hole was the only explanation, with Sir Roger Penrose receiving the other half for the discovery that black hole formation is a robust prediction of general relativity. Decades of painstaking observations tracking stars year after year, measuring their positions with extraordinary precision, proved that something massive and compact lurks at the galaxy's center. no known object other than a black hole fits the observations. The images from the Event Horizon Telescope provided final visual confirmation. On May 12, 2022, the first image of Sagittarius A star was released by the Event Horizon Telescope collaboration, and the image, which is based on radio interferometer data taken in 2017, confirms that the object contains a black hole. We see the shadow. We see the glowing ring. We see light bent by powerful gravity into structures that match theoretical predictions. Black holes are real. Something fundamental about black holes may be changing over cosmic time. New observations reveal that the relationship between ultraviolet and X-ray light in quasars has changed over billions of years, and this unexpected shift suggests the structure around supermassive black holes may evolve with time, challenging a decades-old assumption. Quasars are the most luminous objects in the universe, powered by supermassive black holes accreting matter at prodigious rates. For decades, astronomers assumed the relationship between different wavelengths of light from quasars remained constant. An international group of astronomers has uncovered strong evidence suggesting that the material surrounding supermassive black holes has not remained the same throughout the history of the universe, with findings indicating that the structure and behavior of this matter may have shifted over billions of years. Why would this change? Perhaps black holes in the early universe, forming from pristine primordial gas, differ from black holes that have spent billions of years accreting chemically enriched material. Perhaps the properties of the accretion disk, the temperature and density and magnetic field strength depend on the composition of material falling in. Or perhaps the black holes themselves evolve, spinning up or down as they consume matter and merge with other black holes. These questions point toward deeper mysteries. Where did supermassive black holes come from? How did they grow so massive so quickly? Supermassive black holes typically take billions of years to form, but the James Webb Space Telescope is finding them not that long after the Big Bang before they should have had time to form. Observations show massive black holes existing less than 1 billion years after the Big Bang. Standard astrophysics cannot explain this. Black holes grow by accretion, but accretion has a natural speed limit. Radiation pressure from hot gas falling in pushes against additional infalling material, slowing the growth. Even accounting for mergers between black holes, building billion solar mass black holes in such short timescales seems impossible. This suggests something different happened in the early universe. Perhaps the first black holes formed not from collapsing stars, but from direct collapse of massive gas clouds. Perhaps dark matter played a role, concentrating ordinary matter into regions that collapsed directly into black holes without first forming stars. Dark matter could have helped make supermassive black holes in the early universe, according to recent theoretical work. The connection between dark matter and black holes remains speculative, but something allowed supermassive black holes to form far earlier than expected. Return to the photon ring for a moment. The ultimate goal is to observe a photon ring, the place where light orbits closest before escaping around the black hole. And capturing an image of the photon ring would enable scientists to put Albert Einstein's general theory of relativity to the test. The photon ring is a laboratory for testing general relativity in the most extreme conditions. The ring's size and shape depend only on the black hole's mass and spin, not on the surrounding gas or magnetic fields. The relative sizes of successive ring images depend on the black hole spin, and since the diameter of the main emission ring has been measured by EHT, a photon ring diameter measurement by B checks will constrain spin. Future telescopes aim to resolve the photon ring's substructure. MIT Lincoln Laboratory is leading a laser communications team to develop the long-distance high-rate downlink needed for the Black Hole Explorer mission to discover and measure a black hole's photon ring. The Black Hole Explorer mission, if funded and launched, would observe from space, avoiding atmospheric distortion that limits ground-based observations. These high data rates will enable scientists to image the photon ring structure of a black hole for the first time, according to mission scientists. Detecting the photon ring subrings requires extraordinary angular resolution. Using the Event Horizon Telescope, astronomers have achieved very long baseline interferometry test observations at 345 GHz, the highest resolution such observations ever obtained from the surface of Earth. And scientists estimate that the breakthrough will result in a remarkable 50% increase in detail sharpening images and observations of black holes. Moving to higher frequencies from 230 GHz to 345 GHz sharpens the resolution. This is the first time the VLBI technique has been successfully used at a frequency of 345 GHz, and while the ability to observe the night sky with single telescopes at 345 GHz existed before using the VLBI technique. At this frequency has long presented challenges. The challenge is water vapor in Earth's atmosphere. Water vapor in the atmosphere absorbs waves at 345 GHz, much more than at 230 GHz, weakening the signals from black holes at the higher frequency. Observations must wait for exceptionally dry weather, particularly at high-altitude sites. The Atacama Desert in Chile, home to several EHT telescopes, offers some of the driest air on Earth. The summit of Mauna Kea in Hawaii provides another excellent site. Antarctica, despite its harsh conditions, offers extraordinarily dry air and contributed crucial baselines to the first black hole images. Think about the scale of these observations. Radio waves arriving from a black hole 27,000 light-years away. These waves traveled for 27,000 years, crossing the galaxy, passing through clouds of gas and dust, finally reaching Earth. At each telescope, they are captured, their arrival times recorded to within microseconds. Hard drives ship around the world. Supercomputers correlate the signals, comparing the precise timing from each site. From this mountain of data, images emerge showing structure at the scale of 20 micro-arcseconds. 20 micro-arcseconds is incomprehensibly small. It is the angle subtended by a human hair seen from 10,000 kilometers away. It is the angle between two objects separated by the width of Earth's orbit around the Sun, as seen from another galaxy. This is the resolution achieved by the Event Horizon Telescope, and it is barely enough to resolve the black hole shadow and photon ring. Why does any of this matter? Beyond the sheer intellectual achievement, beyond the technological marvel of turning an entire planet into a telescope, beyond the aesthetic beauty of seeing something previously invisible, these observations tell us about the fundamental nature of reality. Black holes are predictions of general relativity. Einstein's equations describe how mass and energy curve space-time, and space-time curvature tells matter how to move. In regions of extreme density, the equations predict singularities, points where curvature becomes infinite, where physics as we know it breaks down. Black holes are the most accessible example of these singularities, shielded by event horizons, but nevertheless real objects in our universe. The images confirm Einstein's predictions with stunning precision. We were stunned by how well the size of the ring agreed with predictions from Einstein's theory of general relativity, according to scientists on the EHT team. The shadow size matches theoretical predictions to within measurement uncertainty. The ring's asymmetry matches expectations for a rotating black hole. The magnetic field structure fits models based on general relativistic magnetohydrodynamics. Every detail so far aligns with Einstein's century-old theory. This agreement is remarkable because general relativity is a classical theory. It does not include quantum mechanics, yet it accurately describes black holes, at least their exteriors, even though we know a complete description requires quantum gravity. The singularity at the center surely involves quantum effects. Hawking radiation definitely requires quantum theory. The information paradox emerges from the conflict between quantum mechanics and classical gravity. Yet, for describing the observable features, the shadow and ring and jet, Einstein's equations work. This tells us something important. Whatever the correct theory of quantum gravity turns out to be, it must reduce to general relativity in appropriate limits. String theory, loop quantum gravity, and other candidate theories all satisfy this requirement. They modify general relativity at extremely small scales or extremely high energies. But for macroscopic black holes far from the singularity, they give the same predictions as Einstein's theory. Black holes also teach us about quantum mechanics. The information paradox forced physicists to confront how quantum theory operates in curved spacetime. The resolution still being worked out in detail involves holography, entanglement, complexity, and other concepts that push the boundaries of our understanding. Information does escape a black hole, so if you jump into one, you will not be gone for good. With particle by particle, the information needed to reconstitute your body will re-emerge. This sounds like science fiction. If I fall into a black hole, I will be destroyed long before reaching the event horizon, torn apart by tidal forces if the hole is small, or I will survive to the horizon only to be crushed at the singularity if the hole is large. Either way, my body is obliterated. Yet somehow, over the incredibly long timescale of black hole evaporation, trillions of years for a solar mass black hole, and much longer for supermassive ones, the information that defined me gets scrambled into the Hawking radiation. In principle, though not in practice, someone could collect all that radiation and reconstruct every detail of what fell in. Does this mean I survive? Not in any meaningful sense. The information is preserved, but the pattern is destroyed and redistributed. It would be like burning a book and claiming the book survived because the smoke and ash contain the information. Technically true. Practically meaningless. You cannot read the smoke. Yet this distinction matters for physics. Information conservation is not about preserving things we care about. It is about preserving the fundamental quantum state of the universe. The laws of physics are time reversible at the quantum level. Given the complete quantum state now, you can, in principle, calculate the state at any past or future time. Black holes threatened this principle. If they destroy information, then time evolution is not reversible. You cannot reconstruct the past from the present if information has been lost. The resolution preserves reversibility, though at the cost of introducing scrambling so complex that practical reconstruction becomes impossible. This brings us to consciousness and observation. Black hole complementarity suggests reality depends on perspective. The infalling observer and the outside observer have mutually inconsistent descriptions of where information is located. Both descriptions are correct within their domains of validity. They do not contradict because the domains do not overlap. The two observers cannot compare notes. This echoes something from quantum mechanics. The measurement problem. Before measurement, a quantum system exists in a superposition of multiple states. Measurement collapses the superposition to a single outcome. But what constitutes measurement? When does collapse happen? Different interpretations of quantum mechanics give different answers, yet all make the same predictions for observable outcomes, because observers cannot compare their experiences across branches of the wave function or between the interior and exterior of a black hole. Perhaps reality is fundamentally observer-dependent in a precise physical sense, not a vague philosophical sense. Perhaps the universe does not have a single God's eye view description, but rather a collection of complementary descriptions that fit together in subtle ways. Black holes might be showing us this feature in its most extreme form. Let me bring this back to the images themselves. When you look at the pictures of Sagittarius A* and M87*, you are seeing light that traveled across vast distances. Light that was emitted by gas so hot it glows in radio wavelengths. Gas swirling at relativistic speeds around objects from which nothing can escape. You are seeing space-time itself bent into a ring. You are seeing the shadow cast by gravity. These are not artists' conceptions or simulations, though simulations guided their interpretation. These are actual observations. Real photons that traveled from near the black hole to Earth, captured by radio dishes, processed by algorithms, assembled into images. We are living in the era when humanity first saw black holes, not indirectly through their gravitational effects on stars, though that evidence was crucial. Not theoretically through mathematical solutions to equations, though theory predicted what we would find, but directly, observationally, undeniably. We saw them, the implications ripple outward. If we can image black holes, what else becomes possible? Can we watch matter falling in real time? Can we see the moment a star is tidally disrupted? Can we observe jets launching? Can we test whether general relativity holds in even more extreme conditions, closer to the horizon than current images resolve? Future observations will push deeper. In coming years, scientists expect to collect more data of SGR A* and other black holes as the EHT expands, adding more telescopes to its virtual array. More telescopes mean more baselines, more ways to measure correlations between signals, better reconstruction of images. Higher frequencies mean better resolution. Longer observation campaigns mean better constraints on how structures change over time. Sagittarius A* remains challenging because it varies so quickly. SGR A* is changing over minutes, so the data is jumping all over the place, which is the fundamental challenge in imaging this black hole. The gas orbits the black hole in minutes. Bright spots appear and disappear. The ring's brightness distribution shifts. Capturing this dynamic behavior requires observations that can track changes on minute timescales, far shorter than the hours-long integration times used for the first images. M87* is steadier, taking days for material to orbit, making it an easier target for detailed study. While the size of the black hole shadow did not change between 2017 and 2018, the location of the brightest region around the ring did change significantly, with the bright region rotating about 30 degrees counterclockwise to settle in the bottom right part of the ring at about the 5 o'clock position. Even M87* shows variability, but on longer timescales that are easier to track. Scientists hope to eventually measure the spin of black holes from their images. Spin affects the shape of the shadow and photon ring. A rapidly spinning black hole has a smaller, more asymmetric shadow than a slowly spinning one. The spin also determines how much energy can be extracted from the black hole, how powerful its jets can be, and how it grew over cosmic time. Measuring spin requires resolving finer details than current images show, but future observations should achieve this. The inner shadow, the dark region within the direct emission, also carries information. Emission typically extends down to the event horizon in the equatorial plane of the black hole, giving rise to a brightness deficit within the direct image of the equatorial event horizon. And this image feature is known as the inner shadow, and also encodes properties of the space-time geometry. Where the inner shadow appears depends on the observer's viewing angle and the black hole's spin. Future multi-wavelength observations combining radio images with X-ray and optical data will constrain these properties more tightly. The discoveries keep coming. Every new observation, every improvement in resolution, every extension to new wavelengths reveals additional layers of complexity. The environment near black holes is not simple. It is turbulent, magnetized, relativistic, and dynamic. It is a laboratory where matter and energy behave in ways never seen anywhere else. Consider the timescales involved. The formation of these supermassive black holes spans billions of years. They grew from smaller seeds, perhaps intermediate mass black holes, perhaps direct collapse black holes, accreting gas and dust and stars, merging with other black holes when galaxies collided. The total luminosity from an outburst estimated to be 1,000,000 times stronger than the current output from SGR A star is comparable with a typical active galactic nucleus. Sagittarius. A star is quiet now, consuming relatively little matter, but it may have been far more active in the past, glowing brightly as an active galactic nucleus when more gas was available. The life cycle of a black hole extends far into the future. Hawking radiation causes even supermassive black holes to evaporate eventually, but the timescale is incomprehensible. A solar mass black hole would take 10 to the 67 years to evaporate. A supermassive black hole like Sagittarius A star would take 10 to the 100 years. For comparison, the current age of the universe is less than 10 to the 10th years. These black holes will outlast stars, galaxies, perhaps everything else in the universe. They will be the last massive objects remaining, slowly leaking Hawking radiation into an empty, cold, dark cosmos. Unless something else happens first. Black holes can merge. When two spiral together and collide, they release energy in gravitational waves, ripples in space-time itself. Intermediate mass black holes weighing 100 to 100,000 times. The mass of the Sun have only been directly detected once before by LIGO last year. The LIGO and Virgo detectors have observed dozens of mergers between stellar mass black holes. Future space-based detectors like LISA will observe mergers of intermediate and supermassive black holes, events that produce gravitational waves with longer wavelengths and immense power. These mergers are violent beyond description. Two black holes, each warping space-time around them, spiral inward. As they approach, their event horizons distort, stretch, reach toward each other. At the moment of merger, the horizons touch and fuse. The combined black hole rings like a bell, its horizon oscillating, emitting gravitational waves as it settles into a new equilibrium. The total energy released can exceed the mass energy of several suns, radiated away in seconds entirely as gravitational waves. We have not yet detected gravitational waves from supermassive black hole mergers. These events should produce the strongest gravitational wave signals in the universe, but their frequencies are too low for current detectors. Pulsar timing arrays, which monitor the precise timing of pulses from distant pulsars, may soon detect the background hum of gravitational waves from countless supermassive black hole mergers across cosmic history. Finding individual merger events will require LISA or similar space-based detectors. Imagine witnessing such a merger with both gravitational wave detectors and the Event Horizon Telescope. We would see the black holes spiral together in gravitational wave data. We would see their shadows merge in radio images. We would observe the combined black hole settle into its final state, its ring stabilizing, its jets perhaps reigniting or intensifying from the influx of energy. This multi-messenger observation of a black hole merger remains a dream for now, requiring capabilities beyond what exists today, but nothing in physics forbids it. Black holes connect to the largest structures in the universe. They sit at the centers of galaxies, their masses correlated with the masses of their host galaxies' bulges. This suggests black holes and galaxies co-evolve. As galaxies merge, gas funnels toward the center, feeding the black hole, triggering bursts of accretion that light up quasars. The black hole's jets and radiation heat surrounding gas, regulating star formation, influencing how the galaxy evolves. The relationship is reciprocal and complex, still being unraveled through observations and simulations. The cosmic web, the largest structure we know, consists of filaments and sheets of galaxies separated by vast voids. Black holes inhabit the densest nodes in this web, the galaxy clusters where hundreds or thousands of galaxies congregate. The most massive black holes, the true supermassive monsters weighing billions of solar masses, live at the centers of the largest elliptical galaxies in cluster cores. These black holes likely grew through countless mergers, inheriting the accumulated mass from each progenitor. At the smallest scales, black holes reveal quantum mechanics. Near the event horizon, virtual particle pairs pop into existence from the quantum vacuum. One particle falls in, the other escapes as Hawking radiation. This process connects the physics of the very large gravity and cosmology to the physics of the very small quantum fields and particles. Black holes are bridges between these realms, places where we cannot ignore either. Physicists hope black holes will point toward quantum gravity, the long-sought theory unifying general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches all aim to describe physics at the Planck scale, 10 to the minus 35 meters, where both gravitational and quantum effects are strong. Black hole singularities are one of the few places in our universe where Planck-scale physics matters. Understanding what happens at the singularity requires quantum gravity. But we cannot observe the singularity. The event horizon shields it from view. This is the cosmic censorship hypothesis, the idea that singularities are always hidden behind event horizons, never naked and exposed to the outside universe. Most physicists believe cosmic censorship holds, though proving it remains an open problem in general relativity. If it is true, then we can never directly observe Planck-scale physics, at least not in black holes. Yet indirect evidence might emerge. Perhaps quantum gravity effects alter the structure of the event horizon slightly. Perhaps they change the spectrum of Hawking radiation in subtle ways. Perhaps they leave imprints in gravitational waves from mergers. Finding these signatures requires exquisite precision, but if we knew what to look for, we might glimpse quantum gravity's effects, even without observing the singularity itself. This is the frontier where physics stands now. General relativity describes black holes brilliantly. Quantum mechanics describes matter and radiation brilliantly. But combining them remains beyond our reach. Black holes, especially their interiors, sit squarely in the gap between these theories. They are the signposts pointing toward deeper understanding, if we can read them correctly. Looking at the images of Sagittarius A star and M87 star, knowing what they represent, fills me with a sense of intellectual vertigo. We are seeing objects that warp space-time so severely that time itself stops at the event horizon. We are seeing light that bent around these objects following curved geodesics, arriving at Earth from paths that would have been impossible in flat space-time. We are observing matter in its death throes, spiraling inward toward oblivion, glowing incandescent before vanishing forever from our view. And somehow, through centuries of mathematics and physics, through decades of technological development, through years of careful observation and analysis, we brought these impossible objects into focus. We saw them, we measured them, we tested our theories against reality and found them holding. This is the power of science, the cumulative work of thousands of minds building on what came before, pushing always toward greater understanding. Black holes are no longer purely theoretical. They are observed facts. We have photographed them. We have detected their gravitational waves. We have watched stars orbit them. We have measured their masses and spins and distances. They are as real as planets and stars and galaxies, strange and extreme as they may be. What comes next? More observations, better resolution, more telescopes, higher frequencies, longer campaigns, images that show finer details, track faster changes, reveal deeper structures. Perhaps we will see tidal disruption events in real time, watching as a star approaches, stretches, breaks apart, forms an accretion disk, brightens dramatically, then fades as the debris is consumed. Perhaps we will catch jets launching, see the base where they form, understand how magnetic fields collimate and accelerate the flow. Perhaps new theoretical insights will emerge from the data. Anomalies that do not quite fit general relativity, signatures of quantum effects, hints of new physics waiting beyond the horizon. Or perhaps general relativity will continue to succeed perfectly, reinforcing our confidence in Einstein's century-old vision. Either way, black holes will continue to surprise us. They are doors to the unknown, objects at the edge of our understanding, testing grounds for physics in its most extreme regimes. They connect microscopic quantum phenomena to cosmic-scale gravitational dynamics. They challenge our intuitions about time and space and causality. They force us to confront the limits of knowledge itself. If you have followed this journey through observations and theory, through images and equations, through paradoxes and resolutions, you have glimpsed what fascinates physicists about black holes. They are not just strange objects in distant galaxies. They are keys to understanding reality at its deepest level. They are problems that demand solutions we do not yet have. They are invitations to think harder, look closer, push further into the unknown. The universe contains mysteries beyond number. Black holes rank among the most profound. We finally saw them. We measured their shadows. We traced their magnetic fields. We tested our theories against their reality. And in doing so, we discovered that nothing makes sense in the comfortable way we expected. Space-time is curved. Information is preserved but scrambled. Horizons hide singularities. Quantum mechanics and gravity clash and merge in ways we are only beginning to understand. This is physics at its best. Observation driving theory. Theory predicting observation, both iterating toward deeper truth. Black holes are laboratories we cannot visit, experiments we cannot control, yet we learn from them nonetheless. They teach us about the universe by simply existing, by being what they are, impossible objects made real by the mathematics of gravity. If you found wonder in these cosmic mysteries, if the images of black holes resonated with something in your curiosity, know that we are living in an extraordinary time. The questions are profound. The observations are unprecedented. The answers are emerging, slowly, carefully, built from countless small insights that gradually cohere into understanding. Thank you for exploring these ideas, for contemplating the incomprehensible, for joining me at the edge of a black hole as close as observation allows. The universe is vast and strange and beautiful. Black holes are among its strangest, most beautiful features. We are privileged to live in an age when we can finally see them, when the invisible becomes visible through human ingenuity and persistence. If these mysteries speak to you, more wait to be explored. The cosmos holds deeper questions, stranger objects, phenomena even more extreme than black holes if such things exist. The journey continues, and perhaps wherever you are in space and time, under whatever sky, you will look up and wonder what else remains hidden, waiting for the right question, the right instrument, the right moment of insight. Until then, fellow traveler, may your sense of wonder never diminish. May you always find beauty in complexity, and may the universe continue revealing its secrets to those patient enough to listen.